All right, in this video, we're going to discuss chemical shift and the nuances that we need to be familiar with. Now, chemical shift essentially refers to where the proton shifts on the scale from the ppm standpoint. Okay, and there's some terminology to be familiar with here, so let's correspond that. Let's say that you have electron withdrawal away from a proton. That's going to cause the proton to have a larger chemical shift, higher ppm, and that's going to cause it to shift further to the left in the spectrum if it has some withdrawal. Signals shifting further to the left are said to be more downfield. In other words, they are more deshielded. Kind of have a summary of that right here. Those signals shifting further to the left are said to be more downfield. They have a higher frequency of resonation. They're more deshielded. That means that there's a small local magnetic presence, and there would be a larger difference between alpha and beta spin state energy. Okay. Now, compared with that, let's say that there's some electron donation directly towards a proton set, or it's just existing in an alkyl dense environment. Those protons are going to be said to be more shielded. When protons are more shielded, they're said to be shifting more upfield, and that would be representative of signals appearing further to the right in the spectrum. If signals are appearing further to the right, they're said to be more upfield. They have a lower frequency of resonation. They're shielded by the local environment, which is present. There's a lot of local electron density, and then there's a small difference between the alpha beta spin state energies. Now, what's important with chemical shift is that we classify protons on sp3 carbons with this minutia here. We're going to say that a proton is on a carbon, and whatever that carbon is directly bonded to, that has the largest effect on the chemical shift. Whatever atom is bonded further than that, that's going to have a more minimal effect on chemical shift. So, for example, if I'm looking at this molecule, I would say that proton type D is a proton on a carbon connected to an oxygen, whereas proton type C, that's a proton on a carbon neighboring a pi system. The pi system is going to have kind of a mild inductive effect, whereas maybe the oxygen, we could say, has more of like an intermediate effect in terms of withdrawal. Then protons A and B I'd kind of classify similarly in that they're a proton on a carbon bonded to an adjacent sp3 atom, and they're shifting more upfield comparatively. So notice that B is pretty far upfield, and while there's an oxygen nearby, notice for B, it's a proton on a carbon directly bonded to another sp3 carbon, and then you have the oxygen. And because the oxygen is not directly bonded to the proton's carbon, its effect is more minimal. I can't stress that enough. Okay. So you need to be familiar with these terms: upfield, downfield, deshielded, shielded, and to basically have those details associated with what does it mean to be downfield? What does it mean to be upfield? Okay, got to have that terminology down. If we were to look at a quick example here for terpial acetate, I would say that the more downfield shifting signal is B, and the more upfield shifting signal is A. Notice that proton type B is a proton on a carbon directly adjacent to the pi system experiencing a mild withdrawal, and proton type A is a proton on a carbon neighboring another sp3 carbon. The oxygen would be then the next attachment and therefore has a minimal effect, and because of this, B is more downfield shifting. Now, to stipulate one little detail that sometimes can be helpful, and this is assuming we have the same splitting pattern. So because these two signals have the same splitting pattern, we can actually use the height of the peak as a metric for the number of protons, meaning this is a smaller peak, and there's less protons making that signal. There's a larger peak, so there's more protons making that signal. But again, you can only use that height at the peak as a metric for the number of protons if the splitting pattern is the same. If the splitting pattern is not the same, we can't do that. Okay. So we said that for protons that are on an sp3 carbon directly, we want to classify them based upon what the carbon is directly bonded to. For protons on sp2 atoms, it's a different story, and we'll talk about that in a minute. So I know it kind of sucks to memorize chemical shift values, but ultimately it's so important when reading spectrums. Breaking this down for you, in that 0 to 1.5 range, you have a proton on a carbon that's just neighboring another sp3 hybridized carbon. I call those saturated protons. They shift 0 to 1.5. In the range of 1.5 to 2.5, sometimes upwards of 3 potentially, you have protons on a carbon neighboring a pi system directly. So it could be neighboring, say, a C double bond O directly, neighboring a benzene ring, even neighboring an alkene. And you'll notice that in this range, we also have an alkyne proton, which tends to be around 1.9-ish. Okay, protons on a carbon neighboring a pi system, we'd say there's kind of a mild electron withdrawal effect by the pi system. Then we have this range of 2.5 to 4.5. This is where you'd have protons on a carbon connected to some electronegative atom, where Z could represent a chlorine, bromine, iodine, oxygen, nitrogen. Now, the halogens, chlorine, fluorine, bromine, and iodine, tend to have more variable shifts in that region. But within that region, nitrogen and oxygen have pretty consistent shift ranges. A proton on a carbon bonded to nitrogen would shift the signal 2 to 3, and then the oxygen would shift that proton 3 to 5. And the reason for that being that oxygen is more electronegative and nitrogen is less electronegative. Okay, at UNC specifically, professors love this distinction of proton on a carbon bonded to nitrogen versus proton on a carbon bonded to oxygen. So we want to know those chemical shifts for sure, and we'll practice that later on when we look at spectrums. All right, so those are protons on carbons that are sp3. Their signal is dictated by what the carbon is immediately bonded to. Then we get into this kind of discussion of protons that are directly on sp2 hybridized atoms, like protons on an alkene, proton on a benzene ring. Or you could look at the sp2 sp2 oxygen of phenolic OHs, the sp2 oxygen of a carboxyl group, the sp2 nitrogen of an amide, or we could have, say, a proton on the sp2 carbon of an aldehyde. Now, you'll notice that the most downfield shifting type of proton characteristically is a carboxylic acid. Aldehyde protons are around 10, phenolic OHs are around 9, and then amide NHs, or the hydrogen on a C double bond O adjacent to a nitrogen or even an oxygen, that's going to be around 8. The vinyl region will be 4.5 to 6.5 protons on an alkene. The benzene region is 6.5 to 8 approximately. Now, what I want to point out specifically is that the OH protons here and the NH protons there, they're on sp2 atoms. And when you have an oxygen or nitrogen that's sp2 with a proton, those chemical shifts are a little bit more predictable. However, if you were to look at, say, an sp3 oxygen bonded to a proton, or even an sp3 nitrogen bonded to a proton, okay, those chemical shifts are a lot more variable, 2 to 7. So a lot of variability if the nitrogen's sp3 bearing a proton. Same can be said for an sp3 oxygen bearing a proton. So this is so important. You want to be able to classify protons down to this minutia. I swear it's so important. And please note that everything is kind of in relationship to a reference signal. When you're looking at what is actually defining 0 in H1 NMR, it's this molecule tetramethyl silane. Remember that silicon as an atom is less electronegative than carbon. And being less electronegative than carbon, silicon actually donates. There's this inductive donation towards those methyl groups. And because of that donation, those methyl groups are very, very shielded. And the spectrum is calibrated to have the 0 reference point be defined by TMS, and everything else is in relationship to that. So if you ever see silicon, think silicon is actually directly shielding protons, and those would be the most upfield shifting type of protons. Now, I want to quickly discuss why protons on sp2 systems appear especially far downfield, while, say, a proton on an sp carbon appears more upfield comparatively. This has to do with a phenomenon called diamagnetic anisotropy, which is a fancy way of saying that the pi magnetic field, which is independent of the sigma field, is creating its own local magnetic environment, and that's having an effect. Now, specifically, when you're looking at, say, your aryl protons, your vinyl protons, or an aldehyde proton, those are protons on an sp2 pi system, okay, on a double bond. And during the subjection of that compound to the radio wave in our H1 NMR spectrum, what's going to happen is the induced pi magnetic field, which is our diamagnetic anisotropy, that's going to align directionally with the applied magnetic field. And remember, if we're adding to that applied magnetic field given by big BO, that causes an additional de-shielding effect. And because of that additional de-shielding effect, we see protons on sp2 atoms, double bonds of a benzene ring or an alkene or, say, an aldehyde, being really, really far downfield. That induced pi field causes an additional de-shielding effect. However, the opposite is true if we're on a triple bond. If the proton is on a triple bond, I want you to think the induced pi magnetic field, the diamagnetic anisotropy, takes on a different kind of shape, and because of that different shape and orientation, it actually ends up being subtractive from the applied magnetic field. It subtracts and causes a net shielding effect. In other words, protons on a double bond would cause de-shielding, would experience a de-shielding because of that pi system, but protons on a triple bond would experience, conversely, a shielding effect. And that's why you saw the alkyne shifting around 1.9, whereas the sp2 atoms had that pi de-shielding effect, sending them more downfield. Okay? All right, so now what we're going to do is we're going to practice chemical shift. So as we're ranking protons in their chemical shift, we're thinking that the most downfield shifting protons with the largest ppm are probably on sp2 atoms. And we're seeing here that A and E are on sp2 atoms. The carboxyl group will be around 12-ish. That'll be the most downfield shifting. Then we'd have the aryl proton. Aryl protons directly on the benzene ring will shift 6.5 to 8. From there, looking at the remainder, I'm seeing that B is experiencing de-shielding from the oxygen and from the benzene ring. B will be next most downfield. And then D is a proton on a carbon adjacent to a pi system. That should shift 1.5 to 2.5, sometimes upwards of 3. And that will be more downfield than proton type C, which is just a proton on a carbon connected to another sp3 carbon. Now, looking at proton type B for a second, if you just had the oxygen, that would shift maybe 3 to 5, but having a proton attached to a carbon, which is having withdrawal from the pi system of the benzene ring and the oxygen, it's maybe at the tail end, closer to 5 of that region, so the effects can be additive, in other words. All right, so we'll start looking for sp2 atoms. Those would be the most downfield, and then from there you would check to see what inductive effects are present. Here we had the oxygen making it more downfield than D, and D has the pi system making it more downfield than C. Looking at our next structure, starting with the most downfield shifting proton, I'm seeing that proton type C here is on an sp2 hybridized carbon, and the others are not. So C would be the most downfield. And notice that's technically aryl as opposed to vinyl. So that would be 6.5 to 8, and that's because this is an aromatic ring. Okay, aryl essentially just means aromatic ring, like a benzene ring, or here this is a pyrrole ring, which is aromatic, 6.5 to 8. From there, I would say A is more downfield than D. So consider this with me. If that C double bond O wasn't there, then I would say D is more downfield than A, because D is affected by the oxygen, and if the C double bond O isn't there, then A is just impacted by the nitrogen, and oxygen shifts further than nitrogen. However, because the C double bond O is there, proton type A is experiencing the inductive effect from the nitrogen and from the C double bond O, and that's probably enough to push it further downfield than proton type D. But again, if that C double bond O wasn't there, then D would likely be more downfield than A. Okay, a little bit of a nuance there. From there, I would say B and then E. B is a proton on a carbon neighboring a pi system, 1.5 to 2.5, which would be more downfield than E, which is just a proton on a carbon neighboring another sp3 hybridized carbon. Okay. All right. So the other thing I want to show you really quickly here is, let's say that you had this structure here, and we compared it to this structure here. And we're specifically looking at that proton versus these protons. From a classification standpoint, each of those are protons on a carbon bonded to an oxygen. So we could say their electronic effect is similar. Now, when electronic effect is similar, but you're looking at a CH2 versus a CH, there's actually going to be a small difference in chemical shift. So assuming that proton kind of magnetic environment is similar in that fashion, a CH is going to appear more downfield, higher ppm than CH2, and CH2 would appear more downfield than CH3. Again, this is assuming that the electronic effect is similar from a classification standpoint. If that's true, then the CH is more downfield than the CH2, and the CH2 is more downfield than the CH3. So only apply that idea if the magnetic effects are similar from a classification standpoint. Okay? Now, the other nuance I want to talk about really quickly with chemical shift is chemical shift on a benzene ring. Okay, before we get into these two examples here, let's say that you had a substituent that simply had an inductive effect, like halogens. They don't have a resonance withdrawal here. There's just a sigma electron withdrawal effect. I would say that a proton closer to the chlorine would appear more downfield than one further away. Okay, now that's pretty intuitive, right? Proton closer to the inductive effect is more downfield than one further away. But that's only an analysis we can make in terms of distance from that substituent if it's an inductive group. But consider this with me. Now that you guys have talked about, benzene EAS and donation and withdrawing substituents, we're going to say that if you have a resonance withdrawing substituent, it's not just about proximity to that C double bond O now, it's really about where charge is created. Now, if you were to withdraw from the ring and you drew out the resonance structures, you draw out all the resonance structures, and then you compile a hybrid identity, what we'd see is that predictably, at the ortho position, adjacent to our substituent in the para position all the way across, we'd have positivity there. And because of that positivity, the protons at the ortho position and at the para position are actually going to be more de-shielded and have a higher ppm shift than the protons at the meta position. Kind of a funky idea, but we'd say because the meta position is not getting that positivity, the meta is going to be more upfield than the ortho and the para positions. In other words, the para position, which is further away, is more de-shielded than the meta position. Okay, I'm going to repeat that one more time. Because the positivity lands at the para position, I would say that the para proton is more de-shielded and appears more downfield than the one at the meta position, which is technically closer. But at the meta position, we are not receiving the positivity, and therefore there's less de-shielding. Okay. Now on the flip side, let's consider a resonance donating group like maybe this nitrogen. With the nitrogen directly attached to the ring, it resonance donates into the ring. And predictably, at the ortho and para positions, we see charge created when we look at the overall hybrid. And you'll notice now that charge is a negative charge. And with the negativity landing at the ortho and para positions, that now means that the ortho and para positions are more shielded than the meta positions. So comparatively, because the meta is not receiving that negative, the meta positions and the protons there are technically now more downfield than the ortho and para positions. And this is because having negativity land at the ortho and para carbons is leading to a direct shielding at those ortho and para positions. So in other words, if you're ever ranking protons directly on a benzene ring and you see a substituent that would either resonance withdraw or resonance donate, what I want you to do is put charge at the ortho and the para positions. If it's a resonance withdrawing group, you put positivity at the ortho and para positions, and those protons at the ortho para positions would be more de-shielded. If you have a resonance donating substituent, I want you to annotate negativity at the ortho and para positions. And now with negativity, those protons are now more shielded. Okay. Now, ultimately, we'll talk more about chemical shift when we get down into the further pages where we, match protons and spectrums and when we get to structure elucidation. But I can't stress enough that your knowledge of this chemical shift chart will be crucial as you read spectrums and fully have to deduce the identity of a compound from the spectrum. We want to get down to this minutia of what is the proton's carbon directly connected to if we're looking at an sp3 hybridized carbon. And then we acknowledge that protons on sp2 atoms appear more downfield comparatively